All right, and then just closing out with some basic definitions regarding waves, but these are very important. So the first is something we've actually talked about before this year, which is the period of something repeating. Okay, so things that repeat periodically, the period itself is just the measure of time it takes for it to repeat. So for example, here we have a pendulum. Okay, if we start the timer here at the top, then we can stop it when it's right back to the same spot. Okay? Notice the period would not be when it starts and then over here when it reaches over here, because that's not repeating. We have to wait until it comes back. Now that's the period. So if we were to time it and then stop it there, that's the period of that. Okay, because we're measuring time, then the time for one oscillation, that's going to be measured in seconds. So period, which is capital T, is measured in seconds. The inverse of that would be frequency. So frequency is not how long it takes, but how many times it repeats every second. So the unit for frequency is 1 over seconds, or what's known as hertz. Okay? So how many times does it repeat per second? Okay? So maybe this, if we want to simplify it, let's say it repeats like 1 time every second, so then the frequency would be just 1 hertz. Okay? Or we could say it repeats once every 2 seconds, so then that would be 0.5 hertz. Once every 3 seconds, that's 0.33 hertz, etc., etc. Once every 5 seconds, that's 0.2 hertz. Okay, so how often does it repeat and how many seconds? So once every 10 seconds, once every 20 seconds, once every whatever. That's going to be your frequency. Okay. And it could be for anything that's repeating. So here we have like this spring here, and it's the exact same thing. So how often does this repeat every single second? Let's say this repeats 2 times in 1 second, then that would actually just be 2 hertz. Okay. And then our first equation for this unit is going to be the equation for period. So like we said, period is the time it takes for one oscillation. So the variable for period is just capital T, which is a measurement of time. Okay. Capital T is measured in seconds, and period is literally just the inverse of frequency. So period is 1 divided by the frequency, and frequency is therefore 1 over the period. If you have 1, you basically just flip it, and now you have the other. Okay? So F equals 1 over T, T equals 1 over F. They're just inverses of each other. And like we said, frequency is measured in hertz. Okay. All right, and then just wrapping up with a couple more definitions. So in terms of wave velocity, for waves, we already know the wave period is just the time it takes for a wave to repeat. Okay? The wave frequency is the number of waves per second. So how many waves happen in that second? Maybe 1 wave, maybe half a wave, etc., per second. Okay? Here we're making just a little note, which is that once a wave is produced, the frequency doesn't change, and we'll see why that's important when we start studying light and color. But just to have in your notes, that frequency does not change once a wave is generated. So wavelength could change, and the speed could change, but the frequency doesn't change. Okay, and then just repeating that wavelength, like we said, is the distance from one point to the next repeating point. So for example, crest to crest, compression to compression, trough to trough, rarefaction to rarefaction, etc., etc. Even midline to the same repeating point on the next wave counts. Okay. All right, and then the last new piece of information is just how do you actually calculate this velocity of a wave. Okay? So the velocity is just going to be, just like we did before, we had displacement over time, or speed was distance over time. For waves, it's going to be the same logic, but using different definitions. So for wave, instead of distance over time, in a wave, the distance is actually just the wavelength, which is this little banana shape here. That's lambda. Okay, so that stands for the wavelength. So this is how long the wave is. Okay, so that's basically our distance when we're talking about waves, and it's just distance over time. But once again, when we talk about waves, the time is how long it takes to repeat. So that's actually going to be the period. So speed, distance over time, is actually just wavelength divided by period. And if that's all you remember, then that's actually all you need to be able to calculate the speed of a wave. Okay. They chose here to simplify it, and this is actually a very popular simplification of this equation. So instead of saying 1 over the period, we actually just saw that 1 over the period would actually just be the frequency. So then if we go back one more time, we could say distance over time, or instead of saying 1 over time, we could just say frequency times the wavelength. And I'll repeat that one last time. So 1 over time is basically just frequency. So you could literally just write F times the wavelength. instead of 1 over t times the wavelength, because those are the exact same things anyway. Those are inverses of each other. Okay. And then we just wrap up with a little bit of practice. So you can pause here and try these problems out for yourself. Okay. And then we can just quickly go through them together as well. So what is the speed of a water wave with a wavelength of 10 meters if it has a frequency of 0.15 hertz? Okay. So the speed of a water wave, we already know, is just going to be the frequency times the wavelength. So this is going to be 0.15 times 10. That's going to be 1.5 as our answer, meters per second. Next. A man on a beach notices that 4 waves arrive on the shore every 20 seconds. And he wants to know what's the frequency of these waves. So 4 waves every 20 seconds tells me that there's 1 wave every 5 seconds. So 1 over 5 seconds, that's going to be 0.2, and that is 0.2 hertz as my frequency of these waves. Okay. So these waves repeat every 0.2 hertz, or repeats once every 5 seconds. So 1 over 5, that's 0.2. Third is a sound wave travels from air to metal. So it's sound, which is longitudinal. It goes from air to metal, so it's going to something more dense. What happens to its speed as it makes this change? So because it's going from something less dense to more dense, and it's something that depends on the medium, then this should actually speed up. So the speed actually increases for this sound wave going from air to metal. Okay. And then lastly, why is the sound from a speaker louder when you sit closer to it? So why is the sound from a speaker louder when you sit closer to it? So the sound itself is going to dampen. Okay? So the sound starts off with a high amplitude, but realistically, because of friction, the wave is just going to get less and less energetic, and it's just going to go down in sound and energy as it goes further and further away. Which is, once again, if I'm speaking to you and you're really close to me, you're going to hear me the loudest, but as you move further and further away from me, you're going to hear my voice dampen more and more and more. At some point, you're not even going to be able to hear me talk, even if I just keep on speaking at the same volume. And that's just because sound dampens due to friction. So if I'm sitting closer to it, I should be hearing it louder. If I'm sitting further from it, then I should be hearing it lower. So the wave has more energy when it's closer, or higher amplitude. Okay? And that's about it. So from here, you can move on to doing the practice set. That's going to be it for waves. We're going to talk about wave properties tomorrow.